Please remember to subscribe to this channel and to like the video if you wish to see more content of this nature. Welcome to Power Machines N5. Today's presentation is going to be on enthalpy and steam. This is a very important module for anybody that is doing power machines. The reason for that is because the stuff that we are going to introduce in this module is all going to serve you for the rest of your power machines journey. What I mean by that is that in Power Machines N5, throughout the course, you will be doing enthalpy in different modules. And also in Power Machines N6, you will again find enthalpy in the modules that you will be dealing with in Power Machines N6. And I have seen so many students in N6 who struggle to understand some of the modules, and I can see that the issue is because they never really understood enthalpy in Power Machines N5. And so pay attention to this module, listen to my explanations closely, because if you understand this very well, it will help you throughout your journey in power machines, okay? So this is relevant for somebody who is doing power machines N5, but also for someone who is doing power machines N6 if they never really understood enthalpy while they were doing power machines N5. Let's begin. So, as an introduction, the first thing that I am going to tackle is the difference between temperature and heat. Many people use these two terms interchangeably, but in reality, as an engineer, you need to understand that there is a difference between temperature and heat. Temperature is simply a measure of how cold or how hot something is. That is what temperature is, okay? A measure of how hot or how cold an object or a substance is. That's it. That's what temperature is. However, heat is energy, okay? More specifically, a flow of energy that occurs from an object or a substance that is at a higher temperature towards a substance that is at a lower temperature. That is what heat is. Heat is energy, a flow of energy between two objects that are at different temperature. Okay, so this is very important for you to understand. Why? Because if you think that temperature and heat are the same thing, then you will have a tendency to assume that if temperature is rising, it means that heat is being added, which is true in most cases. But then you can also think that if temperature is constant, that means that no heat is being added. And that can be wrong in some cases, okay? Because you can have a situation where you are adding heat and yet the temperature is not changing, okay? So it's important for you as an engineer to understand that temperature and heat are not the same thing, okay? In most cases, temperature will respond to heat, but you do have certain cases where you could be changing the heat value that you are adding, and yet the temperature remains constant, okay? So just bear in mind now that heat and temperature are not the same thing. So even when I am going to be explaining this module to you, when I speak of heat, do not think of temperature. Think of it as energy, okay? A flow of energy from a substance or an object at a higher temperature towards one which is at a lower temperature. So when I speak of heat in my explanations, do not think of temperature. I am talking about energy, okay? If I want to speak of temperature, I will say temperature, okay? Because the two are not the same. As an engineer, you need to understand that difference. So the next thing I am also going to point out in this introduction is the concept of specifics. For instance, if I say specific enthalpy, what is meant by that? Well, when I say specific enthalpy, what I mean is enthalpy per unit mass. So you take the enthalpy and you divide it by the mass, okay? So for instance, enthalpy, we use the letter H, okay, capital H. That is the letter we use to represent enthalpy, and the unit for enthalpy is kilojoules, okay? And so specific enthalpy, we will use the letter small h, okay? And the unit will be kilojoules per kg, because remember what I said, to use specific enthalpy is enthalpy per unit mass. And this doesn't just apply to enthalpy, okay? The concept of specifics apply to any quantity that you can have. For instance, entropy. If we say specific entropy, what we mean is entropy per unit mass. So the symbol we use for entropy is the capital letter S, and the unit is kilojoules per Kelvin. Okay, and so specific entropy will use the letter small s, okay? And the unit will be kilojoules per kg Kelvin. You can see that we've divided this unit per kilogram, okay? Because we're dividing the entropy by the mass. That is what specific entropy is. It's entropy per unit mass, okay? So what I want you to notice is that when we deal with specifics, we divide by the mass. And also the symbol that we use moves from being a capital letter to being a small letter. Okay, very important. One last example could be specific volume, okay? Specific volume, again, will be volume per unit mass. So now for volume, we use the letter capital V to represent volume. The unit for volume is cubic meters. And so specific volume will be cubic meters divided per kilogram, because we divide the volume by the mass. And the symbol that we use is small v, okay? Because with specifics, we use small letters to represent them. Very important. And so let us now look at enthalpy. What is enthalpy? Enthalpy is basically a measure of the heat content of a system, okay? So if you take all the heat content of a system, that is what enthalpy is, okay? And the equation for enthalpy is given by this. So H, which represents enthalpy, is equal to U plus the product of P and V. So what is U? U is the internal energy, okay? P is the pressure and V is the volume, okay? So if you add to the internal energy the product of the pressure and the volume, what you will get is enthalpy, okay? Very important. This is the equation we use to calculate enthalpy. And now specific enthalpy will be given by this equation here. And I want you to appreciate that I am no longer using capital letters, but rather small letters, because each of these are specifics, okay? So specific enthalpy will be equal to the specific internal energy plus the pressure multiplied by the specific volume, okay? Very, very important. So this is the equation you will use to find the specific enthalpy. At this point, it's important for me to also point out that sometimes you will find a question where they say to you to find the enthalpy. And so how will you do that? Well, you will just multiply the specific enthalpy by the mass, okay? So enthalpy is also equal to the specific enthalpy multiplied by the mass, okay? So you can use this equation if the data in the question allow you to do that. But if not, if what you have is a specific enthalpy, to get the actual enthalpy, you need to multiply that specific enthalpy by the mass. And you need to remember that enthalpy is heat, okay? As I gave you a definition of it here, enthalpy is a measure of the heat content of a system. So in some questions, they may ask you to calculate the heat. And if you have specific enthalpy, then what you can do is just multiply it by the mass to get the heat, okay? Because the actual enthalpy is also the heat content of the system. Very, very important. And so now we will look at steam generation. What you see here are the labels that I am going to be introducing to you shortly and what they mean. Okay, so if you just lost in my explanation and you can't remember what a certain label meant, you can just read it from this here. Okay, all the labels are here. But please, for now, listen to me very carefully because I am going to give you all the explanation about the different types of enthalpies. And so first, let us begin with a graph that plots pretty much temperature versus enthalpy. Okay, so on the x-axis, what we will have is enthalpy. And then on the y-axis, what we have is the temperature in Celsius degrees. Okay, very important to specify that. Okay, so the temperatures we have on the y-axis are in Celsius degrees. Okay, and on the x-axis we just have enthalpy. Okay, the unit for enthalpy in this case doesn't really matter. Okay, as far as the explanation is concerned, but what does matter is that the temperatures that we have on the y-axis here are in Celsius degrees. Okay, and of course what we have here is the 0 degrees, which is here, and it's also this point is also the point for zero enthalpy. Okay, so that is where we start. And now the temperature that is the most important is what we will refer to as the saturation temperature. Okay, TS, and it is also the boiling point. So if I say saturation temperature or boiling point, it's one and the same thing. Okay, so TS that you see here is the saturation temperature of the water, and you can also think of it as the boiling point of the water. And now somebody may ask me, why is it that you didn't just write 100 degrees? Because water boils at 100 degrees. The reason for that is because water does not always boil at 100 degrees. Water boils at 100 degrees if the pressure that you have is atmospheric pressure. Okay, if you change the pressure, the water will boil at another temperature. Okay, the reason we were taught in primary school that water boils at 100 degrees, it's because the pressure that we have in everyday life is the pressure of the atmosphere. It's atmospheric pressure. And so for that reason, the water that we will deal with in real life will generally boil at about 100 degrees. But if you create a situation where the pressure that you have, the ambient pressure that you have, is not 100, is not 101.325 kilopascals, which is atmospheric pressure, if you create a situation where you have a different pressure than that of the atmosphere, the water will not boil at 100 degrees. It will boil at another temperature. And so for me to be safe, that is why the boiling temperature, I'm just going to call it TS, which is also the saturation temperature. Okay, it's one and the same thing. Okay, I'm not going to say 100 because, as I explained, water does not always boil at 100 degrees. It boils at 100 degrees if the pressure that you have is atmospheric pressure. If you're dealing with a different ambient pressure, the water is not going to boil at 100 degrees. So we have this zero temperature here, and also we have the boiling temperature there, or the saturation temperature. And I drew a horizontal line to just show you where that temperature is. Now, the next thing that we're going to plot is actually the graph that water will describe, okay, as you increase enthalpy in the water. In other words, as you raise heat in the water, this is how its temperature will behave. Okay, it will describe this graph here. And so I am going to explain now in details. I want you to pay close attention to me. So the first phase that we have is liquid. Imagine that you have water in a pot and you have put it on a stove, okay? And now you turn on the stove and the plate is now getting hot, and now that water is now beginning to get hotter and hotter. So initially, the water that you have in your pot will be liquid, okay? And this is the place where the water is liquid. And so initially, the temperature is at 0, and you are increasing the temperature as the heat is increasing. And that is why it is describing this graph, because when the temperature is here, you have this much heat in the water. When you increase the heat to here, the temperature of the water now becomes somewhere there. And of course, this water that you have in your pot will remain in the liquid state until it reaches the boiling point. When the water reaches the boiling point, now the water in the pot will no longer just be liquid, but you will have gas also that begins to form, okay? But from the place where the temperature is 0 in the water to the boiling temperature of the water, the state of the water is just liquid. And the amount of heat that you need to provide to the water to raise it from 0 to boiling temperature, that heat is what we call HF, okay? So HF is the liquid enthalpy, okay? And it is also referred to as the sensible heat, okay? These two are one and the same thing. If you find sensible heat in your question or you find liquid enthalpy, they refer both to HF. And what is HF? HF is the amount of heat that you need to provide to the water to raise its temperature from 0 to the boiling temperature. And I repeat again, that boiling temperature is not always 100 degrees. It's only 100 degrees if the pressure that you're dealing with is atmospheric pressure. If you're dealing with a situation where the pressure is maybe 600 kilopascals, water is not going to boil at 100 degrees. It will boil at a much higher temperature than 100 degrees. Okay, so HF is the heat that you need to provide to the water to raise its temperature from 0 to boiling temperature. Okay, I hope that is making sense. So in this first phase, the water in your pot is just liquid. But once it begins to boil, okay, it gets into a phase where you begin to have a mixture of liquid and gas. And that is where we say that it is wet, okay? It's wet steam because the steam that is generated is a mixture of liquid and gas, okay? And that will continue to happen until you no longer have any liquid in your pot, because if you continue to add heat, eventually all the liquid that was there will become gas, okay? And so when that point is reached, this is what we call dry saturation, okay? The dry saturation point is the point where you no longer have any liquid, but all the liquid has been turned into gas, okay? So initially you had just liquid and no gas. You added heat in that water to the point where the water began to boil. And the heat that you need to provide to the water to raise its temperature from 0 to boiling temperature, that heat is called HF, which is liquid enthalpy or sensible heat. And then once you reach the boiling point, at this point here, you now begin to have gas forming in your pot, okay? So now what you will have is a mixture of liquid and gas. And that is why we say that the steam is wet, okay? And then if you continue to add heat, you will eventually reach a point where you no longer have any liquid. Now, all the liquid will be turned into gas, and this gas is going to be dry, okay? And that is the point of dry saturation, okay? Very important. And so what I want you to see here is that from the moment the water begins to boil to the moment it reaches dry saturation, okay, the temperature of the mixture is not changing, although you are increasing heat. And so this goes back to prove that heat and temperature are not the same thing. Because from the moment the water begins to boil, though you are adding more heat to the water, the temperature of the water is not changing. And that will continue to remain constant until all that water is turned into dry saturated gas. Okay, where there is no more liquid, it is just dry gas. Okay, when we reach that point, this is what is referred to as dry saturation. And so the heat that you need to add from the boiling point for you to reach dry saturation, this is what we refer to as HFG. Okay, this is the heat that you need to add to the water from the time it begins to boil for it to reach dry saturation. In other words, for all the liquids to be evaporated and the dry to be made and the gas to be made dry. Okay, I hope this is making sense. So the heat that you need to add to the liquid from the moment it starts boiling, for all the liquid to be evaporated and the gas to become dry saturated, okay, that heat that you need to add is this here, and this is what we refer to as HFG. And this is the enthalpy of evaporation. Okay, so this is the heat that you need to completely evaporate the liquid. Okay, from the moment it starts boiling, the heat that you need to add to completely evaporate it from the moment it starts boiling, this is HFG. Okay, it's called the enthalpy of evaporation, and it is also called the latent heat. Okay, so these two expressions are for HFG. Okay, they are used interchangeably. You are just supposed to be familiar with them both. Okay, very important. And so HF that we saw earlier was the heat to take the water from 0 to boiling temperature. That is HF. And then once you've reached boiling temperature, the heat that you need to add again for the liquid to be completely evaporated and the gas to become dry saturated, that heat is HFG. Okay, and so if we want to know what will be the heat that we need to take it from 0 to dry saturation, then that will be the sum of these two, okay, as you can see, and it is called Hg. Hg here is the enthalpy of dry saturated steam. Okay, that is Hg. And as you guessed, Hg is simply equal to Hf plus HFG. So that is the amount of heat that you need to provide to water that is at 0 degrees for it to become completely evaporated and the gas to be dry saturated. Okay, the heat that you need to provide from here to there, this is Hg. Okay, it's the enthalpy of dry saturated steam. Very important to understand that. And once we are here, okay, the heat, once we are here, of course, the gas is dry saturated. But if we are anywhere in between boiling point and dry saturation, the gas is wet. Okay, it is a mixture of gas and liquid. Okay, so the steam is wet in between boiling point and dry saturation. Let's say if we pick a point there, okay, you can see that blue dot here. If we pick a point here, the state of the steam here will be wet, okay? And so the heat that you have from the boiling point to that random point in the middle of the boiling and dry saturation points, that heat is a fraction of HFG, okay? That is why we say that it is equal to XHFG, okay? And this X here is just a fraction, and it is called the dryness fraction. It is always smaller than 1. Okay, because if this was bigger than 1, it will go beyond dry saturation. It has to be smaller than 1 because HFG is this, And so you need to multiply HFG by a number smaller than 1 for you to get a fraction of HFG. Okay, so this fraction factor is called the dryness fraction. X is the dryness fraction. So for instance, if they say to you that X is equal to 0.92, it means that the wet steam that you have here is 90% dry, so it's close here, okay? It's 92% dry. If they say to you that X is equal to 0.92, it means that the dryness fraction of this wet steam is 92% dry. So it's almost completely dry. Completely dry, it's when it reaches dry saturation. That is 100% dry. But anywhere in the middle here, it is less than 1. So X will be less than 1 anywhere in the middle because it's not 100% dry in the middle. It is 100% dry here at dry saturation. So if you are given a dryness fraction of X is equal to 0.92, what that means, it means that the wet steam here is 92% dry. So it's almost completely dry. Or you can also say it is only 8% wet, okay? So as we are moving from the boiling point to the dry saturation point, the dryness is increasing and the wetness is reducing, okay? So the dryness fraction increases as you get closer to dry saturation, and the wetness of the steam decreases because it is being evaporated. Okay, I hope this is making sense. And so if you are told that the dryness fraction is 0.92, that means that the wet steam is 92% dry, or it is only 8% wet. Okay, and so this is what this X represents. Okay, so now if we want to know the heat that we need to take the water from 0 to this place here where it is wet, that heat will be HF plus XHFG. As you can see, this XHFG is the heat that you need to add beyond boiling point for you to reach this point here where it is wet. But the heat that you need in total from 0 to this place where it is wet is going to be the sum of HF plus XHFG. And so this is what we call HW, and this is the enthalpy of wet steam, okay? HW, it's the enthalpy of wet steam. Now, what if we continue to add heat to the steam once it is dry saturated? What will happen? Well, it turns out that when you reach dry saturation, if you continue to add heat to that dry saturated steam, what will happen is that again the temperature of the steam will begin to rise, okay? Once we reached boiling point, although we were adding heat, the temperature was remaining constant until we reached dry saturation. But once you reach dry saturation, if you continue to add heat to the steam, the temperature of the steam will rise, okay? And so let's pick a point. Of course, this is HW, it's equal to HF plus XHFG, okay, as I was explaining earlier. Okay, now back to what I was saying. Let us pick a point in this region. And of course, in this region, you can expect the steam to just be a gas, and it is superheated, okay? What is meant by superheated gas? Superheated gas, it's gas that is at a temperature greater than saturation temperature or boiling temperature. If the steam is at a temperature that is greater than the boiling point or the saturation temperature, so any point here will be superheated, okay? And so if we pick a random point there, represented again by the yellow dot, you can see that its temperature here, which is TSUP, to just say temperature of the superheated steam, you can see that this temperature is greater than saturation temperature. It's greater than the boiling point, okay? So any steam that is at the temperature greater than boiling point is superheated. Okay, and so the heat that corresponds to that kind of superheated temperature is here. Okay, if you draw a vertical line down to the enthalpy axis, you will be at this point, and you can see that we've added heat beyond dry saturation, because dry saturation stops here, and so we've added heat beyond dry saturation, okay, to be able to achieve that temperature. And so the heat that is added beyond dry saturation is given by this equation here. Cp that you see is the specific heat capacity of superheated steam. TSUP is the superheated temperature of the steam, and TS is the saturation temperature or the boiling temperature, okay? And so the heat that is added beyond dry saturation is Cp multiplied by Tsap minus Ts, okay? This is what it is. So now, if we want to know the amount of heat that we need to add to the steam from 0 to the place where it is superheated, that total heat, that is what we refer to as H-sap, okay? H-sap is the heat from 0 to the place where it is superheated. And as you can see, if you look carefully at this diagram, you will see that it is actually equal to Hg plus Cp multiplied by Tsap minus Ts. And so that is the equation for H-sap. It's equal to Hg plus Cp multiplied by Tsap minus Ts. Okay, so I hope this made sense. Okay, if you did not understand my explanation here, you are welcome to rewind the video and watch it as many times as possible, because this understanding of enthalpy is really important for the rest of your Power Machines N5 course, and even in Power Machines N6. Really, really important. And so to drive the understanding, we will present you with steam tables. Now, steam tables, you will usually find them at the back of your Power Machines textbooks, okay? And when you go to write your exams, they give you steam tables in a booklet, okay? And this is what they look like. You have, first of all, the steam table that is useful when you're dealing with steam that is not superheated, and it looks something like that. And then you have steam tables that are used when you're dealing with steam that is superheated, and those tables look like this, okay? And it's very important for you when you're reading a question to know which of the steam tables you're supposed to use. And that is just down to you being able to understand whether the steam you're dealing with is superheated or not. If the steam you're dealing with is not superheated, you will look at these tables that look like this. But if the steam is superheated, then you will have to consult these tables. And in the superheated steam tables, you will see that you can actually read the value for the superheated, the enthalpy of superheated steam, okay, H-sap, okay? You can find that you can read it in your tables for superheated steam. But now, I just gave you an equation for you to actually be able to calculate it. Okay, in the previous slide, I told you that H-sap is equal to Hg plus Cp multiplied by Tsap minus Ts. Okay, we just saw that equation. But then again, when you have the superheated steam tables, you can actually read the value in the table. Now, the question is when to use the equation to get H-sap and when to use the table to get H-sap. And by the way, here it's HSU. They didn't say SAP, but it's the same thing, okay? HSU is H-sap. Okay, so when do you read the value from the table and when do you use the equation for you to get H-sap? The answer is simple. If you're dealing with a question where you are not given Cp, okay, then you have to read H-sap from the table, okay? So read H-sap from the table if Cp is not given in the question. But if they give you CP in the question, then find H sub using the theoretical equation that are presented to you earlier. Okay, so you only read H sub from this table if CP is not provided in the question. If CP is provided in the question, then to calculate H sub, you need to use the equation that I showed to you. Why it's better to use the equation if you can? It's because it gives you a more accurate answer. These values in the table are experimental, okay? So you only rely on experimental values if you cannot get the exact theoretical value from the equation, okay? Very, very important. So I repeat, you read H sub from the table, okay? Only if CP was not given in the question. Now, let us look at some examples. During a process, steam at a pressure of 500 kilopascals is heated to a temperature of 375 degrees. The specific enthalpy is then 3,220 kilojoules per kg. Determine the mean value of the specific heat capacity during the process. So that's the question. You're welcome to pause the video here and read it again. Now, how do you solve a question like this? First, you have to see what is given to you. They've given you the pressure of the steam, okay, is given. And they also gave you the temperature of the steam. And they told you the specific enthalpy is this. So now they want you to find the specific heat capacity during the process. So first we need to consult our tables to establish whether we're dealing with steam that is not superheated or it is steam that is superheated. And how will you know that? I explained earlier that if you have steam that is at a temperature greater than saturation temperature or boiling temperature, if you have steam that is at a higher temperature than boiling temperature or saturation temperature, then that steam is superheated. So we are given in this question the pressure at which the steam is 500 kilopascals. So from the steam tables, we can find the saturation temperature for steam at 500 kilopascals. So if you look at the steam tables here, this is 500. Okay, that row there is for 500, and you can see that TS for 500 is 151.8 degrees Celsius. That is the boiling temperature for when the pressure of the steam is 500 kilopascals. It's 151.8. But here, this steam is at 375. So you can see that the temperature at which the steam is here is much greater than the saturation or boiling point temperature of the steam. So this steam here is superheated, okay? And so because it is superheated, we have to use the formula for superheated steam enthalpy, okay? The enthalpy of superheated steam. And so T sub is therefore 375 degrees, okay? Because this is a superheated temperature, it is greater than saturation temperature. So T sub is 375 degrees. We know the formula for superheated enthalpy. In this question, we are given the specific enthalpy already for this steam is this, and since this steam is superheated, therefore this enthalpy is superheated enthalpy. And it is given by this equation here. And in this question, what they want us to find is CP, okay, the specific heat capacity for this steam, okay? Since this steam is superheated, we need to find the specific heat capacity of superheated steam, this CP here. And so what is Hg? If you look at the table here, you will find that at 500 kilopascal, Hg is 2747. Okay, so we will plug it in here. Of course, H sub is 3,220. And we're trying to find Cp. T sub is 375. The saturation temperature or boiling point temperature is 151.8. Okay, so we have everything here to be able to calculate CP. So if we plug in the numbers, you can see the only thing that you do not have is CP. And you can then solve for CP and you will find it to be 2.119 kilojoules per kg degrees Celsius. Okay, that is the unit for CP. Whether it says degrees Celsius or degrees Kelvin, it's one and the same thing. Okay, and so CP is this, okay, and the unit for CP is that here, kilojoules per kg degrees Celsius or degrees Kelvin. Okay, it's the same thing. So this is all you had to do for this question. Let us look at another example. Now, in this example, they say that you need to determine the state of the steam. Question 1, when the steam is at its saturation temperature and a pressure of 250 kilopascals, and the specific enthalpy is 2690 kilojoules per kg. Okay, so we need to determine the state of the steam. If the steam is at its saturation temperature and the pressure is 250, and the specific enthalpy is 2690 kilojoules per kg. Question number 2, we need to determine the state of the steam if the pressure is 800 kilopascals and the temperature of the steam is 250 degrees. Okay, so let us do this question. What is meant by you to when they ask you to determine the state of the steam? What do they mean by that? They simply want you to tell them if the steam is wet or if it is superheated or if it is dry saturated. Okay, so that's what they want to know. When they tell you to determine the state of the steam, they want you to tell them if it is wet or if the steam is dry saturated or if it is superheated. Okay, so for the first question here, we need to look at our table, okay? And so we have the table there, okay? Or should I say a portion of it? And here, the steam is at its saturation temperature and a pressure of 250 kilopascals. So when you look at the pressure of 250, you are here. So we can pretty much put that in that box, okay? So this is the row that is going to be of interest to us because that's why you have a pressure of 250 kilopascals, okay? And so in this case, you are told that this steam is at its saturation temperature, okay? However, the specific enthalpy is 2690 kilojoules per kg. Okay, so now what do you need to do here for you to determine the state of the steam? You need to compare this specific enthalpy to that for dry saturated steam, okay? Because the heat, if you add more heat to dry saturation, then you fall in the zone of superheated steam, right? And so remember the graph that I had. This is what we had in one of the previous slides. Okay, and so you can see here dry saturation is at Hg. Okay, Hg is where you have dry saturation, and so when we have a pressure of 250 kilopascals, Hg is 2716. Okay, so this point here is 2716, but the one we are given in the question is 2690, which is here, somewhere here, okay? That's where you will have 2690. It's somewhere here because this is smaller than 2716, which is Hg, okay? And so you can see that this specific enthalpy is smaller than Hg. Therefore, since it is very close to Hg, it is falling in the wet region. You can see here 2690 here in the wet region. It has to be because it is smaller than Hg. So we can therefore say that this steam is wet because if you have a pressure of 250 kilopascals and you are at saturation temperature and your specific enthalpy is very small, sorry, it's slightly smaller than this than dry saturation specific enthalpy. Therefore, you are here in the wet region. Okay, so the steam is wet. I hope you are able to appreciate this. And so, therefore, it is wet, and the enthalpy of wet steam that we will have will be, of course, 2690, which was given to you. This is the enthalpy of wet steam. You can see that. And so since the state of the steam is wet, what we need to do is to find the dryness fraction. Whenever you have steam that is wet, then you need to calculate its dryness fraction. And so to be able to do that, we will use HW's equation, which is this, and we will read HF from the table, HFG from the table, and we will find X. And so plugging in the numbers, we know HW is this, 2690 will be equal to HF. HF when the pressure is 250, HF is here, 535, plus X, that's what we're trying to find, the dryness fraction, multiplied by HFG. HFG, when we have a pressure of 250, HFG is here, is 2181. Okay, so we multiply like this, and as you can see, the only thing that you do not have is X, and from this you can then derive the value of X as 0.988. So the dryness fraction of the steam is 0.988, and the state of the steam here is wet, because as you can see, its specific enthalpy is just slightly smaller than dry saturation for that pressure and that saturation temperature. Okay, very important. Now for question number 2, we need to find the state of the steam when we have a pressure of 800 kilopascals and a temperature of 250 degrees. Again, you need to look for 800 kilopascals in your table. So this is a portion of the table, and there is 800 kilopascals. Here you can see that. And so if you look here, what is the saturation temperature at 800 kilopascals? It's 170.4. However, the steam that we have is at a temperature of 250 degrees. Okay, so because 250 degrees is greater than the saturation temperature when the pressure is 800 kilopascals, therefore we know that this 250 degrees is actually a superheated temperature. And since it is a superheated temperature, the steam is superheated. Okay, and we can read the specific enthalpy of this superheated steam from the superheated steam tables. And so when we go to the superheated steam tables, a pressure of 800 kilopascals, okay, and a temperature of 250 degrees gives you a value for HSAP of 2951. Okay, you can see here, this is the row for HSAP, and when you have 250 degrees and a pressure of 800, this is the value for HSAP that you have. Okay, so HSU or HSUP, it's the same thing, will be equal to 2951 kilojoules per kg. But what is important to note for that question is that the state of the steam is superheated. Okay, very important. Let us look at one last example. Calculate the saturation temperature and latent heat for steam at a pressure of 222 kilopascals. Question number 2, the heat required to convert 1.5 kilograms of water from 40.3 Celsius degrees to dry saturated steam at a pressure of 600 kilopascals. Okay, so let us do this question. So for the first question, you have to find the saturation temperature and latent heat for steam at a pressure of 222 kilopascals. Okay, so if you look at the table, you will see that in our steam table, we do not have a value for 222 kilopascals. If you look at it carefully here, you will see that you have 220 and after 220 you have 230 kilopascals. So there are no values in the table for 222 kilopascals. So then how will you get the value for the saturation temperature and the value for the latent heat? The latent heat is HFG, the enthalpy of evaporation. How will you get that since you do not have 222 on the table? If it was 220, we will just read it directly from the table. But in this case, it's 222. And we don't have 222 in the table. So we can't read these values from the table. So how are we going to get them? Okay, 222, because it is not on the table. In order for you to get the value for TS for 222 and HFG for 222, you need to use linear interpolation. Okay, linear interpolation is a way of it's a way of estimating what the value will be, okay, for a set of data that you do not have in the table. Okay, it's a way of finding the value for data that you do not have in the table. Okay, basically linear interpolation is pretty much a use of a graphical method to try and estimate what the value will be for a data that is not in the table. Okay, like in this case for 222 kilopascals. And so I'm not gonna bore you with the details. I'm just gonna give you the equation that is going to be useful to you in order for you to actually successfully apply linear interpolation to estimate the value for TS for a pressure of 222 kilopascals and the value for HFG, because HFG, that is the latent heat. Okay, so the equation is this one. Okay, so y is going to be equal to y1 plus y2 minus y1 over x2 minus x1 multiplied by x minus x1. Okay, so this is the equation that we will use for us to be able to estimate a value for TS for 222 kilopascals and for HFG, because 222 is not in the table. Okay, so we can just read it here, but we will estimate it. Okay, and the equation we're going to use is for linear interpolation, and this is the equation in question. Okay, very, very important. So how do you apply this equation? Now let's say this is the table that you're reading, that you're using. Okay, and the value that you have is x1, y1. Okay, these are the values on top, and directly below x1, y1, the value at the bottom are x2 and y2. But now you trying to find a value that is between x1 and x2, okay, so that you can determine y. Okay, so like in this case, if you look here, since we've been told that we need to find the saturation temperature and we have the pressure of 222, so we will look at these two columns. Okay, once looking while looking for the saturation temperature, we will need to look at these two columns, and you can see with the pressure of interest that for which we're trying to find the saturation temperature is 222. But 222 kilopascals is not in the table. What you have in the table is 220, which is going to be our x1. And then below 220, what you have is 230 kilopascals, which is our x2. But what we're trying to find is a value for 222, which is in the middle here. And that is what will be our x, okay? So that we can find y here, because we're looking for the saturation temperature for 222, which is between 220 and 230. Okay, so x will be our 222, and TS for 222 that we're trying to find will be somewhere between 123.3, which is the TS for 220, and 124.7, which is the TS for 230. So y1 is 123.3, y2 is 124.7. But the y we're looking for, which is the one that will correspond to a pressure of 222 kilopascals, will be in between the two. Okay, so I hope this is making sense. And so If we look at these two columns, the one for pressure and the one for saturation temperature, you will see that X1 on the pressure side is 220, X2 is 230, and you will see that Y1 is 123.3 and Y2 is 124.7. But what we're trying to find is Y, okay? This Y will be the TS for a pressure X, which is 222 kilopascals, okay? So X here is in between X1 and X2, and the Y value that we're trying to find for this X will be between Y1 and Y2, somewhere in between, okay? So now that we have these like this, okay, we can then plug in the values in this linear interpolation equation and look for Y, okay? And so if we do that, you will see that Y, okay, which is TS for 222, will be equal to Y1. Y1 is this, plus Y2 minus Y1. This is Y2, this is Y1, okay, divided by X2 minus X1. This is what you have here, okay, multiplied by X minus X1. Now, we know what X1 is, and what is X? As I explained to you, X is the value in between these two values that we trying to do the calculations for, which is in this case 222 kilopascals, okay? Because X1 is 220, X2 is 230, and we're trying to find for 222, which is X, a value in between, okay? The table that we have doesn't have this row, okay? It doesn't have this row, so we're trying to calculate for this row, but we already know that the X is 222, so we're just trying to find the Y. And so plugging in the numbers like that, you find that the Y is this. And so therefore, the saturation temperature for a pressure of 222 kilopascals will be 123.58 degrees, okay? We found it using this linear interpolation equation. The value that you get for Y in this case is what gives you the saturation temperature. And because we also need to find the latent heat, which is HFG, we are going to use again linear interpolation, but this time the rows that are going to be of interest is the row for pressure, because what we have is a pressure of 222 kilopascals, and then we will look at the row for latent heat, or HFG, okay? And so if we do that, here we have pressure and there we have HFG. And this is what we will have. When the pressure is 220 kilopascals, HFG is 2193. You can see it here. When the pressure is 230, HFG is 2189. Again, this is X1, X2, Y1, Y2. But we're trying to find X and Y, which are values in between those two rows. So the X we already know is 222 kilopascals, so we need to find the HFG that will correspond to that value of X. And again, you will use linear interpolation. You will use this equation, plugging in the numbers. And if you do that, this is what you will get. And as you can see here, we have Y1, which is 2193, plus Y2, this, 2181 minus Y1, 2193 divided by X2 minus X1. This is what we have here, multiplied by X minus X1. Again, this X value is the value that you have here for the pressure in between the pressures of 220 and 230, which is 222. Okay, it's in between those two pressures, so that's why we have it in the middle there. And so that is what X is, minus X1, which is 220. And of course, here we had X2 minus X1. X2 is 230, okay? So you just plug in the numbers like that and you will get the value for Y. But in this case, this Y value that you're calculating is for that row, for that column here, okay? And so this Y value is for that column, and so that column is for latent heat, okay? Because we looked at the pressure column and the latent heat column. And so the Y, therefore, that we will get is the latent heat that we're trying to get. And so therefore, HFG will be equal to 2192.2 kilojoules per kg. Okay, very important. This is how you do it. I wanted to show you also how to get values for data that is given to you that is not in the table. What you need to do is to use linear interpolation the way I just showed you. Now, for the second question, we need to find the heat that is required to convert 1.5 kilograms of water from 40.3 degrees Celsius to dry saturated steam at a pressure of 600 kilopascals. And so, if you look at the diagram that we looked at before, that graph, if you look at it, you will see that the values that you read in the table, which, whether it's HF or HFG or HG, all of those values are the heat that you need to provide to the water from 0 degrees. Okay, like for instance, in this case, Hg that you saw in this graph, this value Hg, which is the enthalpy of dry saturated steam, is the heat that you need to provide to water, which is at 0 degrees, so that it reaches the point where it is dry saturated. Okay, so if water is at 0 degree, you need to provide it with this much heat, Hg, for it to reach dry saturation. So this heat is to take it from 0 to dry saturation, okay, Hg. Hg is the heat needed to take the water from 0 degrees to dry saturation. However, in this question, you are told that you have water that is not at 0. This water is already at 40.3 degrees. Okay, so it is not at 0. It is here at 40.3 degrees. And so if you draw a horizontal line until you meet that graph, and then you draw a vertical line to come down here, you will see that this water already has some heat. Okay, there is some heat in the water already. So for you to take it from where it is to dry saturation, you just need to have that much heat. Okay, so it's not from 0. Okay, the heat that you need to take it from 0 to dry saturation, that is Hg that you read from the table at a pressure of 600 kilopascals. Okay, if you read that Hg value at 600 kilopascals, that will be the heat to take the water from 0 to dry saturation. But that heat, that's not what we're trying to find in this question. In this question, we're trying to find the heat that we need to take it from where it is at 40.3 degrees, okay, which is somewhere here, all the way to dry saturation. So we're trying to find that heat here. And as you can see, this heat here from 40.3 to dry saturation will be equal to Hg minus this portion that is there, okay? We will take the value for Hg and we will remove from that portion that is there, because there is already some heat in the water. So to take it to dry saturation, you don't add the whole Hg, but just this segment here. And this segment here is equal to Hg minus that portion that is there. Okay, I hope that is making sense. And so from the table, when you have 600 kilopascals, okay, you can read the value for Hg. Okay, at 600 kilopascals, Hg is equal to 2,755 kilojoules per kg. Okay, that is the value for Hg at 600 kilopascals. But if you look at our graph here, you will see that this Hg, that's the heat that you need to take it from 0 to dry saturation. However, in this question, the water is not at 0. It already has some heat because it is at 40.3 degrees. So the heat that we need to take it to dry saturation is just from here to here, okay? And so this here will be equal to Hg minus the heat that is already in the water, okay? And so how will we get the heat that is already in the water? You have two ways of doing that. You can use the table if the temperature that is given to you is in the table, okay? You can just read the HF in the table for that temperature, because here when it is liquid, the heat that is in the water is HF, okay? And so you can read the HF for a temperature of 40.3 40.3, okay? So if 40.3 is in the steam table, saturation temperature, okay? Remember the second column is for saturation temperature. And so if you have a saturation temperature somewhere in the table of 40.3, you can just read the HF value that corresponds to that, and that will give you the heat that is in the water when the temperature is 40.3. But sometimes you can get a question where they haven't given you a temperature that is in the table, okay? And so if that is the case, then you will have to use an equation. And this is what we're going to get into right now. So for instance, in this case, a temperature of 40.3, if you look in the steam tables, you will see that that temperature is one of the saturation temperatures that you have in the table, okay? As you can see here, you have 40.3 is one of the temperatures that you have in the table, one of the saturation temperatures. So you can just read the heat that corresponds to that, okay? And the heat that you need to read, or the enthalpy that you need to read, is HF, because we are in the liquid segment, okay? And so the HF corresponding to that is 169, okay? So HF at 40.3 is 169. So this is the heat that you already have in the water, and to that you need to add this heat so that you reach dry saturation. And so to find this heat, this is what we are trying to find. You will just do Hg, which is from 0 to that, minus the heat that was already in the water, okay? Which is in this case 169 kilojoules per kg. But let's assume that 40.3 was not in the table. Then how would you get the heat that is in the water at a temperature of 40.3? Then you will use this equation, okay? So you will calculate HF using the specific heat capacity of the water multiplied by that temperature that is given to you. Okay, that is if you couldn't read it from the table. If the temperature was not one of the temperatures you have in your table, then you can just use this equation to calculate HF. And of course, the specific heat capacity of water is 4.187. Okay, you need to know that, memorize that number. And so we will take that, multiply that by the temperature, which is 40.3. And as you can see, even if we did not use the table and used this equation, the number that we get is very close to the number that you read from the table. So if the temperature that is given to you is not the temperature that you have in the table, you can just find the HF corresponding to that using this equation here. The specific heat capacity of water is 4.187, and then you multiply it by the temperature at which the water is, okay? And so this is the heat that is in the water, okay? This is the heat that is in the water. So we need to find, what this question is asking you to find is the additional heat that you need to add to this so that you that you reach dry saturation, okay? The additional heat that you need to add to the 169 so that you reach dry saturation. Okay, now the heat when water is at 0 that you need to add to the water to reach dry saturation is Hg. Okay, so if we take Hg and we remove this, we will remain with the heat that we need from this to reach dry saturation, okay? And so that's what we're going to do here. So that H that you see here, which is the heat that we need to take it from where it is to dry saturation, is just going to be equal to Hg minus HF at 40.3. So Hg, when you're dealing with 600 kilopascals, is 2,755 kilojoules per second, kilojoules per kg. And so from that, you need to remove the heat that is already in the water to find the heat that remains to take it to dry saturation, okay? So if we do it like that, this is what we get, okay? So the heat that we need to take this water, which is at 40.3 degrees to dry saturation, is actually 2,586 kilojoules per kg, okay? That is the specific enthalpy, okay? Or the specific heat, if you want, okay? That is the specific heat. But now, since we are given a mass of water of 1.5 kg, you will remember that heat, actual heat, okay? Specific enthalpy is specific heat. It's heat per kg, okay? But now here, since we have to convert 1.5 kilograms of steam, we need to find the actual heat that is needed for that mass of steam. And so that actual heat is found by multiplying the mass by the specific heat, okay? And if we do that, this is what you will get. 1.5 multiplied by 2,586, that gives you 3,879 kilojoules, okay? So that is the heat needed to take 1.5 kilograms of steam from a temperature of 40.3 degrees to dry saturation, okay? Very, very important. And so at this point, I need to draw your attention to one thing before I finish, that sometimes they will not always say specific enthalpy, but they will say enthalpy, and what is implied is actually specific enthalpy. But at other times, they will be more specific. They will distinguish between enthalpy and specific enthalpy. So it's just up to you to use your deductive abilities to try and understand what is actually referred to when somebody is saying enthalpy. You will see myself also in my explanation. I wasn't always saying specific enthalpy, specific enthalpy. At times I just said enthalpy. Okay, but what was meant was actually specific enthalpy. So you need to use your common sense and deductive abilities to know exactly what is meant when we say enthalpy, okay? In this question, they said to you that you needed to find the heat required to convert 1.5 kilograms of water. Since the mass was given, we could find the actual heat. But if they had not given you a mass, what you will find will just be the specific heat. And the specific heat would have been the same thing as just finding the specific enthalpy needed. Okay, but since they gave a mass, we can go a step further by multiplying the specific heat or the specific enthalpy by the mass to get the actual heat. Okay, I hope this was clear. I hope this video was helpful. And if you wish to get in touch with me, that's my name. I am also on Twitter, which is now called X. You can follow me there. I have some good things that I post from time to time, very inspirational, that can help you with your career, that can help you in life. And you can contact me using the number in the description as well. Please remember to subscribe to this channel. That encourages me to continue to produce more videos like this. Like the video, subscribe. I appreciate that. Thank you so much.